So far we've been learning about t-tests, and we learned how to do independent sample t-test to compare the means of two groups, or a repeated measures t-test where we compare the same group being measured twice. So, I got to be honest, it seems like now you really know everything you need to know for the rest of statistics. You have a way of measuring mean differences. Anytime you have two groups and those groups have a mean, you can do a t-test and you can measure the difference between those two groups. So really, I don't see any reason in going on learning anything more complex, because I think we got this from here. We'll just do t-tests. Now, I should say that there are some limitations to the t-test. For instance, one of the limitations is you can only do two groups. Right? So if you have three or more groups, you couldn't do a t-test. And the other is we can only use one dependent variable. Like if we wanted to know something about the effects of diet and exercise on both weight loss and fitness gains, that would be a really complex model. So you can use t-tests all around. So if I give you an example like this, the Mayo Clinic recommends exercising 2.5 hours per week with moderate aerobic activity. That's for optimal health. And I want you to compare that to a control group. Well, that's easy. You know how to do that. You got a t-test. But I'm also interested in whether doubling the time from 2.5 to 5 hours per week is better than the control group, but also is it better than just exercising 2.5 hours per week? Now I have three groups and three comparisons. So what would you do? Well, this is easy enough. What you're going to do is compare group A and B. You're going to run a t-test between those two groups. And of course, every t-test, we set an alpha level. We'll keep that at 0.05. Then you're going to run a second t-test between B and C. And of course, the alpha level for that test is going to be 0.05. And when you run your third test, you'll compare A and C, and the alpha level for that test is going to be 0.05. You're running three different tests, each of which has an alpha level or an error rate of 0.05. That shouldn't be a problem. Well, let me give you an analogy. Let's say that I'm doing a lottery. It's a very special lottery. Typically, a lottery is a tax on people that are bad at math. But this lottery is pretty cool, because I'm going to be offering a prize of $1,000, and I'm only selling 20 tickets at $10 a piece. Given that setup, what would you do? You buy all of the tickets. If you have all of the tickets, you're guaranteed to win. Each one of those tickets individually has a 1 in 20 or 5% chance of being the winner. But because you control all of the tickets, one will be a winner. You're sure to get that $1,000. That's going to be money in your pocket. Which one is going to be the winner? You don't know, but you don't care. You've got all the tickets. Something has to be a winner. Now that's great for lotteries, but not so great for statistics. Turn that around. You start running multiple t-tests. Every t-test has a 5% chance of being a type 1 error. By running multiple t-tests on the same data, like comparing A and B, and then B and C, and then C and A, you don't keep your alpha level at 0.05. You have probability pyramiding, in which your alpha level goes up exponentially. Let me illustrate this. In the spreadsheet for this week, there is a tab called Pyramiding, and it shows you what happens when we increase the number of groups, which increases the number of comparisons, and what we call the experiment-wise alpha. Experiment-wise means over the whole model. So if we have three groups, it means we're making three comparisons. An alpha of 0.05 for each means that the total overall functional error rate is going to be 0.14. And if we have four groups, experiment-wise alpha jumps to 0.26. At 5, it's 0.4. At 6 groups, or 15 comparisons, the alpha level is 0.54. It's over 50%. It's a coin flip now as to whether any particular test is a type 1 error. Going back to our lottery analogy, every test has a 5% chance of being wrong, just like each lottery ticket had a 5% chance of being a winner. Only now, making errors, that's a bad thing. And you're pretty well guaranteed by doing all those t-tests, you're going to be making type 1 errors. And like the lottery tickets, you won't know which one is the error. And this time you will care because you're publishing these findings and other people replicate the findings. They don't get the same numbers as you do. Come to find out, you were making type 1 errors, saying things were true when they were not true. That could have a devastating effect on your research career. This is not the road that we want to go down. So using multiple t-tests isn't going to work. The good news is we have a solution. That solution is we're going to do something called an ANOVA. ANOVA stands for Analysis of Variance. We are going to analyze the variance between groups with the variance within groups and determine whether there are differences between the means in all of the groups that we are comparing. It is a single test that will look at all of the groups, keep our alpha level at 0.05, and tell us whether there are mean differences that are statistically significant. And just like with t-tests, you can do an ANOVA with 2 groups. You don't have to have 3 or more groups. You can do an ANOVA with just 2 groups. In fact, if you look at the t-statistic that you get from doing that t-test and compare it to the F statistic when you've run an ANOVA test on 2 groups, you will find that the square root of the F value is the t value. With 2 groups, it is the same test. Well, maybe we don't even need t-tests anymore. Maybe we can just do everything with ANOVAs. The t-test is dead. Maybe I'm going a little too quick there. Turns out t-tests are really one of the most popular tests in statistics. Everybody knows how to do them. They're easy to teach. They're easy to learn. They're very common. We use them in a lot of different ways. So long live the t-test. This week, we have a business of the week, which is Gordo's Gym. Gordo, in addition to being a gym owner, is also a statistician, so we're going to be doing some comparisons. We're going to be looking for some group differences. Gordo wants to test the effectiveness of 3 different diets on weight loss for his clients. He randomly selects 20 clients and randomly assigns them to one of 4 diet approaches, 5 in each group. The first group is the control group. It's the willpower group. But then there's 3 other versions of diets, Weight Watcher, Jenny Craig, and Nutrisystem. With that setup, we can talk through the things that we need to know in order to do an ANOVA. So first of all, independent variable. We're not going to call it an independent variable. It's called a factor. When we have 2 independent variables at work, we'll call that a 2-factor ANOVA. This that we're doing is a 1-factor or one-way ANOVA. Factor, that's our independent variable. In this example, it will be type of diet. We have only 1 factor, but type of diet has 4 levels. Each condition of the independent variable factor is called either a level or a treatment. Each of the 4 types of diet approach is a level within our single factor in our one-way ANOVA, which is type of diet. That's our independent variable. The dependent variable has to be something that we can measure, quantify, and calculate as a mean. So the dependent variable has to be a variable that we can measure on a scale level, interval, or ratio. The dependent variable is that scale level, so in our case it'll be weight loss. What we are interested in is whether type of diet affects weight loss. We have effects of each type of diet that we will call treatment effects. Different diets, levels in our factor, lead to different amounts of weight loss, measured in pounds, which is our dependent variable. There's some new letters to know about. The first is the letter K. That stands for the number of levels in a factor. So in our case, we're measuring 4 types of diet. That means K equals 4. Later on, we're going to learn about degrees of freedom. And one of the degrees of freedom is going to be K minus 1, number of levels minus 1. The total number of subjects is N. Everyone who's been included in the research, our total number of participants, that will be N. Anytime we're doing measures, we're going to get some measurement error. We're going to get some randomness, some chance built into our measurements. And what we want to be able to do is separate the chance from the treatment effect, separate the signal from the noise. The symbol for error is E. It's measured by either the mean square within, which is what we'll call it, or you'll see in some textbooks the mean square error. When we do regression equations, we're going to see that error term explicitly listed at the end of the coefficients in our regression equation. Error is something that we need to consider so that we can separate it and sort it out from the actual effects that we're measuring. We have one factor. That's diet approach. That factor has 4 levels for each of the types of diet considered separately. So in our example, K equals 4. The dependent variable is going to be pounds lost. It's a measure. And what we see is that all of these raw data points, that's a measure of number of pounds lost. Collectively, those are the dependent variable. And there's some variability within each group, and there's some variability between those groups. That's the variance that we're going to be measuring. Ultimately, what we'll be able to do is separate the error from the treatment effect, and that will tell us which type of diet is statistically significantly better at weight loss, at least according to this sample. Analysis of variance. We're analyzing variance. Well, where does that variance come from? Like, where are we getting this variance? Like, what is that really? So we need to talk about the sources of the variance. So let's do that. Let's talk about whence cometh the variance. The measure of variance in an ANOVA model is S squared, which some textbooks will call SD squared. In either case, it's exactly the same thing. The variance is the square of the standard deviation. Standard deviation equals the square root of the variance. But what makes this tricky is that even though we're doing an analysis of variance, when you look at the ANOVA summary table, you won't find any column labeled variance. So you need to know what we're calling the variance. Variance in an ANOVA model is called the mean square. And the formula for a mean square is 2 dot plus 2 slash plus square plus crescent. That's a mean square. See, that's a stats joke. It's even better than a dad joke because not only is it funny, it's also nerdy. So that's what makes it cool. Now, speaking of nerdy, this is the guy that came up with this F test that we're going to be using for measuring ANOVA. His name, Sir Ronald Fisher. This guy was a genius. He created not only the test that we're going to learn, but a lot of other, just a true giant in the field of statistics. So you can notice his last name, Fisher, F test, that is where the name comes from. The F ratio, which is the foundation of the F test, is a measure of variance between divided by variance within. Well, how do we separate variance between and within, and where do these variance measures come from? Let's go back to the raw data. In our table, all of these individual numbers are different from each other. All of those differences are the total variance. The total variance can be broken down by group. So if we look in the first group, we see all of those numbers are different. But because we're limiting to one group at a time, that is the variance within that group. It is quantified by the standard deviation, which again, if we square that value, we will get the variance. So there is variance for the first group, the willpower group. There is variance among the second group and the third and the fourth. All of these groups have variance within the groups. And that variance is from error. It's random effects. You have multiple people following different diets, they're losing different amounts of weight. But what we're interested in is the treatment effect, the mean difference of weight loss between the different diets. We're going to take the variance between, which is the treatment effect plus randomness. And we're going to divide that number by the variance within. See, the variance within is just error, just random chance. The variance between contains our treatment effect. But because it also is based on those groups, it also has error. By dividing variance between, which is treatment effect plus chance, by the variance within, which is simply chance, we cancel out the chance, leaving us with only the treatment effect. That ratio is the F-test statistic. Variance within, variance between, there's a lot to keep track of there. So let me use some other examples that might make it easier to understand within and between. Like let's say that we are shopping for pairs of jeans. So you want to buy a new pair of jeans. When we consider cost, there's differences between stores. So if I'm looking for a low-cost jeans, can you think of any place that would sell low-cost jeans? I'm going to a secondhand store, or a Walmart comes immediately to my mind. And then there's more moderate range prices. Maybe there's some places at the mall or some other stores, a little higher quality. And then at least one store at the mall, when my wife and I would walk through the mall, which we do because we're old and we like to walk around inside. As we walked through, I believe it was Dillard's, there were tables with jeans on the table, and those jeans were chained down. I guess they had problems with people stealing jeans. So there were really expensive jeans chained down to the tables. I'm going to say that that store is high priced. There's another store in the mall that's medium, and then there's another store, we'll say Walmart, which is low price. There are differences between. However, is every pair of jeans at Walmart the same price? Or every pair of jeans at that really expensive store the same price? There's some variance within, but ignoring all of that random error, there are some big differences between. That's the treatment effect. That's what allows us in the real world to say, this is more expensive than that store. Another example could be growing crops. We have 3 different types of fertilizer. As you look at a cornfield, is every stalk of corn in that field exactly the same height? There's variance within. At the center of the field, they tend to grow at the best. And as you get off toward the periphery, you get a little shorter crops over on the edges. Maybe it has to do with the amount of rain and the runoff and which ones are getting the most water or the best access to the fertilizer that's being spread. The point is, if you were to take that one seed that had been planted on the edge that didn't grow as well, if that one had been planted in the middle, it would have grown like all the other ones. It's just random chance that it got stuck on the edge and it didn't grow as well, didn't get as much water, didn't get as much fertilizer. Random variability within. But what we're interested in is treatment effect, between. We look at this first field and we see that this corn is growing beautifully. And the third field, also very nice. We're getting some excellent growth from both of those fertilizers, but this middle group, not so good. We are interested in the variance between. The first fertilizer and the third fertilizer give us good results. This middle group, not so much. Or another example might be the temperature of rooms in your house. There's variance within and there's variance between. Variance between. What would be the warmest place in your house? It might be the attic. If you go up in the attic, especially in the summertime, it's really hot up there. And the coolest room in your house maybe the cellar, the basement, especially if your cellar opens with a big hole in the wall open and it's in the Himalayas. You get what you get when you ask AI for examples to use as illustrations. Now, the most comfortable room in the house might be the living room. However, is every spot in the living room exactly the same temperature? I know that it is not, because the Chihuahua always goes and either lays down in the sunshine or in front of the heating vent, and will lay right there with the warm air blowing on her. It's warmer next to the vent or in the sunshine than it is over on the couch. That's where the Pomeranians are. They don't need to be sleeping by the warm air blowing. They'll just sit up on the couch. Now, the whole room is a temperature, but there is variance within that room. However, overall, if I want the coldest room in the house, it's going to be in the basement, the warmest room up in the attic. It's the differences between that are of interest. Ignore all that random variability between the sunshine and the couch. Just focus on the big differences. That's what we're doing with variance within and between. Ignore or control for the variance within so we can really focus on the variance between. We'll take the degrees of freedom for a particular F distribution. And an F distribution will have a critical value, which is set based upon the degrees of freedom. Well, what if there is no treatment effect? What if we're just dividing error by error or chance by chance? If there's no effect, anytime you divide something by itself, you're going to get a ratio of 1. Therefore, this F distribution tends to stack up around a value of 1. If there is a treatment effect, however, we're going to see values greater than 1. And if they get big enough, they'll cross that critical value, they'll jump that fence, and they'll be out here in the region of rejection, which means we're going to reject the null hypothesis that says these means are the same, and conclude that in fact there are mean differences within our model. Now, I've been talking about variance between, variance within, mean squares, probabilities. There's a lot to keep track of, much more so than with our t-test. Therefore, we're going to need a way of organizing all these sources of variance and putting them into a format where we can keep track of what's what. We need to make this a little cleaner. So what we're going to do is create a table. It's called an F table, or an ANOVA summary table. Everything that you see in this ANOVA summary table is exactly right, except for one thing, these numbers in blue. You wouldn't ever include those numbers. I just put those in so that you would know which column I was talking about. So if I say in column 1, our ANOVA summary table tells us the source of the variability, you'll know which column I mean. Sources, between and within. Remember, within can also be called our error term. If you add between and within, you get the total variability. So if you think about columns and rows inside of that raw data that we were looking at, all of that adds up to the total variability. The second column is the sum of squares associated with each source of variability. This you could calculate on your own, but we're going to let the software do this calculation for us. Give us the sum of squares. Degrees of freedom is going to be based on the n-1 idea. So degrees of freedom between is going to be the number of groups minus 1, or k-1. In our case, it'll be 3. The total is 19, which is n-1 for the group. Now, the within degrees of freedom is a little different. That's n-k. The mean square is always a sum of squares divided by degrees of freedom. 24.55 divided by 3 is 8.18. And 7.43 divided by 16 is 0.46. That's the mean square, which you remember, that's the name for the variance. We have variance between and variance within. We're going to divide those. That's where the ratio comes from. So our F value, in this case 17.62, that is 8.18 divided by 0.46. And what that tells us is there is 17.62 times more variability between than there is within. So that's way over the fence. That is definitely statistically significant, and we can tell that as well by looking at our p-value, which is less than 0.001. But we know that probability doesn't tell us the full story. We also want a measure of effect size, and for that we're going to use something called omega squared. I'm going to go into a little more detail about measures of effect size here coming up. I just want you to see where that would be placed within our ANOVA summary table. Now, when I was in graduate school, I took a class on ANOVA. And I got to tell you, I was baffled. I was having trouble following. It was really tough to learn. But on the other hand, I didn't have me as an instructor, so maybe that was it. Here's the point. I was struggling to learn it. And the only thing that I could do to keep track of what's what is I just made a table of where all those pieces fit. And I couldn't keep track of the terminology, so I wrote that in. And I created this table that I would use for all other ANOVA summary tables of calculations and what was what and what divided by what. And so when I first started teaching statistics, I went back through all of my old stats notes, and I found this table when I was looking through my notes about ANOVA, and I thought, I want to include this for my students. So maybe they won't be as flustered by learning this as I was. So hopefully this will make life easier for you. This is like a generalized table. This is to keep track of all the parts and what they are. So for instance, here's your sum of squares between, the SSB. If you're interested in like, what is SSB? It's right here, sum of squares between. And the SSW, that's your sum of squares within, which is the same as the sum of squares error. Everything in the table is listed down below the table, so you know what's what. Degrees of freedom. K minus 1 for between treatments. And remember K, that is number of levels or treatments. And minus K, where N is your total sample size. Add those together, you get the total degrees of freedom. And we just keep working through. Mean square between, mean square within is the sum of squares between divided by the degrees of freedom between. Same thing for within these values. Remember, our F is the ratio of variance between by variance within. Our variance is the mean square. So between divided by within gives the F ratio. P-value is something you're going to have to get from statistical software, but you could calculate your omega squared effect size using other elements from this table. For instance, the sum of squares between is that you find in this second column, sum of squares between. That could plug in, you could solve for the formula for the omega squared. So I hope that you find that table is really helpful and beneficial for you. We've done the hard work of finding whether or not there are differences in our model. So it seems like we could just relax at this point, because if we have statistical significance, we know that one of these groups is truly different. But it's not that easy. You see, ANOVA uses a two-step testing procedure. We can't just do the F-test, there's a follow-up that we need. The way that we will approach ANOVA is, step one, we will do the F-test, which is called an omnibus test. It's looking at the entire model, all of the variance, total, in between and within, and telling us whether or not there are group differences in this model. If the F-test is significant, then we know there are group differences in our model, but we don't know which groups are different. In order to tell which groups are different from which other groups, we're going to have to do a follow-up test. It's called a post-hoc test, where the word post-hoc means after. The post-hoc test will identify which means differ. You don't always need to do a post-hoc test. And the time when you absolutely don't need to do a post-hoc test is if you have a non-significant ANOVA. You only need a post-hoc test if the ANOVA is significant. Well, that's easy enough, right? But actually this can be heartbreaking, because I've had this happen more than once, where I'm working with a student, a grad student, someone working on a dissertation, and they do this ANOVA, and the ANOVA is non-significant. But the fact is that when you use SPSS or JASP or any other statistical software, it's going to run post-hoc tests for you regardless. So what happens is the student will look at the post-hoc tests, and one of those post-hocs will be statistically significant. And the student will say, I know that the overall F-test wasn't significant, but look, there's a significant difference in the post-hoc. And that's the heartbreaking part when I have to explain that those are type 1 errors. If the F-test isn't significant, we don't interpret the post-hoc test. And what looks like significant errors or significant differences, those are really type 1 errors. And the other time you don't need a post-hoc is if you only have 2 groups. You only need a post-hoc test if there are 3 or more groups. If you have 2 groups, that's easy enough. We just look at the 2 means. Whichever mean is higher is statistically significantly greater than the other mean. If you're using an ANOVA like a t-test, we don't need to do a post-hoc. We can simply look at mean differences. Most of the time, however, we'll have 3 or more groups. We'll have a statistically significant F-test, and we will need to do a follow-up test. Now, you remember I told you about Sir Ronald Fisher, the inventor of the F-test. He also invented the first post-hoc test, which makes sense. He created this whole package. We do the F-test, analysis of variance, follow up with a post-hoc test, and that's how we do stats. The test that Fisher designed is called Fisher's LSD test, comparing the means of 3 different groups, all possible pairwise comparisons. Now, when I was a grad student, back in the 90s, we would chuckle when we talked about Fisher's LSD test because we remembered, the hippies in the 60s and 70s dropping LSD and tuning in and turning on and dropping out and getting psychedelic and writing some really good rock and roll music and don't do drugs. The point is this LSD is not that. This is the least significant difference. This is the least difference in mean differences that is statistically significantly different. The logic behind Fisher's LSD is you do an omnibus test. We find out whether differences exist. If the omnibus test tells you that differences exist, you can follow up knowing that there is no chance of making a type 1 error. The F-test has already assured us that these differences truly exist. So we're just going to do a follow-up. We're going to do a comparison of each of the groups, A to B, B to C, C to A, except that actually just turns into a t-test. The type 1 error rate for Fisher's LSD is exactly the same as if we were just running t-tests. The reason I mention that is because our textbook wants us to do Fisher's LSD post-hoc tests. And I've asked them about that. Why are we doing that? And I haven't gotten a good answer. I'll show you how to do it. I just don't recommend doing it. There are too many type 1 errors with Fisher's LSD test. It is not the best approach. And I'm not the only one that noticed that. Others have noticed that there's an increase in type 1 errors. We need to control for that. How can we do that? Carlo Bonferroni came up with the next logical approach. We want our overall test to be 0.05. So we want the total model error at 0.05. If we're doing 3 t-tests, 3 comparisons, all we need to do is divide 0.05 by 3. It's that easy. Instead of using 0.05 for our t-tests, for our follow-up tests, we're going to use 0.0167. That's our new alpha level. Well, that's great. That's sensible. This is still used. Bonferroni corrections are used often. They work for t-tests. They work for ANOVA. They work for chi-square distributions. It's a really flexible test. It's simple. It's easy to understand. But it has a problem. In controlling the experiment-wise error, it overcorrects for type 1 errors. And that means there are more type 2 errors. We have more times of missing an effect that's truly there because it's not simply additive, it's an exponential increase as we add the number of comparisons. So we have more type 1 errors with Fisher's test. We have more type 2 errors with Bonferroni's test. What can we do? This is the follow-up test that I'm going to recommend that we do. Tukey's HSD, where HSD stands for honestly, significantly different. We're still going to compare A to B, B to C, C to A, all of those mean differences. However, when we're using Tukey's LSD, we get the pairwise comparisons the same way we get with Fisher's. We control for the alpha level of type 1 like we would Bonferroni, and there's no loss of power, so we control for type 2 errors. We get honestly significantly different follow-up tests. There's one other thing about the Tukey's though, and that is the formula for Tukey's requires that all of the groups have exactly the same sample size. In our example, we had 20 people divided into 4 groups, so 5 in each group. That's beautiful, but that's because we're doing it in the classroom. In the real world, almost never will you have exactly the same number of people in every group in your ANOVA. And so you can't use Tukey's test. So what John Tukey did was he worked with Kramer, not John Kramer, that's Jigsaw, right? So Dr. Kramer, and came up with a new version, the Tukey-Kramer test, which does work with unequal sample sizes. We're going to use statistical software to do an ANOVA. We're going to ask for a Tukey's post-hoc test. If the group sizes are the same, it'll run Tukey's test. If the group sizes are different, however, it will run the Tukey-Kramer test, and it won't even bother to tell you that. It just does it and gives you the answers. So if you check Tukey's as your post-hoc test, you're going to get exactly what you want for your follow-up with your ANOVA. That's why I recommend using Tukey's. And remember, it's Tukey, not turkey. Now, I mentioned effect size earlier with that omega squared. Let me give you a little bit of background on the effect sizes and how they're used with ANOVA. The first effect size, this is the one that I learned about when I was a grad student, eta squared. Eta squared is the percentage of variance in your dependent variable accounted for by the independent variable. It's called a strength of association test, and it's interpreted in the same way as an R squared. Now, we haven't gotten to regression yet. We're coming to that next in a couple of weeks. When we do a correlation or a regression, we can square the R value, square the correlation, and we use that as an effect size. So it's going to run from 0 to 1, and we'll interpret the closer it is to 1, the stronger the effect. And then we can do exactly the same thing with this eta squared. The closer it is to 1, the stronger the association between the variables. However, eta squared is biased in that it systematically overestimates the true effect size. And it doesn't give us the effect for individual variables, it gives us the model effect size. If you have multiple independent variables, you kind of want to split out which source of variance has what effect size. So the solution there is to use a partial eta squared, which is also a strength of association effect size for ANOVA. It is also interpreted the same way as an R squared, the percentage of variance in the dependent variable accounted for by the independent variable, but it is less biased. Partial eta squared is the effect size that I grew up using, and it's a perfectly serviceable effect size. The limitation is it's really just limited to the sample. So I'm learning the effect size in the sample, but remember, maybe from the first lecture I did, we're not that interested in the sample. We're interested in what the sample can tell us about the population. And this partial eta squared effect size is biased in that it overestimates the population value, the population effect size. Therefore, the measure of effect size that we're going to use is called omega squared. Now, as before, it is this measure of association. However, it is unbiased in that it is giving us a measure of what the effect size should be in the population. We're going to be using either omega squared or partial omega squared. The good news is we can calculate this omega squared from information in the ANOVA summary table. Here's my formula. The first thing I need is the sum of squares between. I can find that in column 3. And then I need the degrees of freedom between. I'll plug that in from column 2. The mean squares within plug in 2 different places. And finally, my sum of squares total plugs in the denominator. I do the math, and I end up with an effect size of 0.311 for this particular example. Those are the fundamentals of ANOVA. So at this point, I know that you're itching to actually do an ANOVA. Let's open up that spreadsheet that I gave you for this week, and I will walk you through an ANOVA by hand. But I'm not actually going to make you do all the calculations by hand. We'll use Excel for doing the math. Moderate regular exercise is linked to stronger bones and muscles, reduced risk of disease, brain health, weight management, and overall well-being. The Mayo Clinic recommends exercising 2.5 hours per week with moderate aerobic activity for optimal health. Alfred Packer eats a high-protein diet and works out regularly at the Donner Pass Fitness Club. He knows that some exercise is better than none, because he's read this article, but he wonders if exercising twice as much as the Mayo Clinic recommends would be twice as beneficial. How can we answer this question? Well, first of all, step one, we're going to make sure that we're using the right statistical test. We have 3 groups: a control group, which doesn't exercise, a second group, which exercises for the recommended 2.5 hours per week, and a third randomly selected, randomly assigned group that exercises for 5 hours per week. And we want to know, is exercising the recommended amount of 2.5 hours better than being in the control group and not exercising? Is 5 hours a week better than not exercising? But also, is 5 hours a week better than 2.5 hours per week? Is doing twice as much as what's recommended a big improvement? With that, we know that we will use a one-way ANOVA or a one-factor ANOVA. The one-factor ANOVA, single-factor ANOVA, one-way ANOVA has one independent variable, which we call a factor. That factor has multiple levels. Those individuals in our levels should be randomly selected and randomly assigned. We can also use naturally occurring independent variable groupings, which we call a quasi-independent variable. So if we were measuring something like smoking, we can't just randomly assign people to smoke a pack a day. What we would do is take people as they come, and those who are smokers, they end up in the smoker group, and those who are non-smokers are in the non-smoker group. We didn't manipulate that. We didn't randomly select and then randomly assign. We just took them as they arrived. So this is a quasi-independent variable, but we can still do an ANOVA with that type of setup. The dependent variable has to be at the scale level. It's quantitative. It's something that we can measure as a mean. And of course, our sample sizes should be approximately equal, roughly equal. If they are too different, then we can increase our type 1 errors, or maybe our results will not be valid. Every test is built on assumptions. We want to make sure our assumptions have been met. There's certain boxes that we can check in JASP when we do it in that other software. To test all of these, we're not going to be able to do that in Excel. We want to check for outliers. That's something we can do even without using software. We want to look for missing data, and if so, we'll either fill in that data or remove the case. And we want to look for independence, except that is really something we're going to do based on our research design. We are designing independent samples. If we wanted to use repeated measures, which of course would violate the assumption of independence, we would then have to use a repeated measures ANOVA. We can still do that, but to use a one-way ANOVA, we have a research design based on independent groups. We also need to test the assumption of normality, and for doing that, we are going to look at the dependent variable. We'll just see whether it is normally distributed. However, you may have heard me say before that the assumption of normality is not that the dependent variable is normally distributed. The assumption of normality is that the distribution of sample means in the population from which the sample is drawn is normally distributed. And of course, the problem with that is we don't have access to the distribution of sample means. So what we do is we use a shortcut. We measure the dependent variable, we check it for normality. If the dependent variable is normally distributed, then what is true of the sample should be true of the population from which it was drawn. In other words, a normally distributed sample is drawn from a normally distributed population. And we know that the distribution of sample means in normally distributed populations will approach normality even for very small sample sizes. Or just check the dependent variable and make sure it's normal, and then you're golden, and you don't have to do anything else after that. The central limit theorem will also come to our aid. The test with the one-way ANOVA is robust for violations of normality, especially if you have groups larger than 30 and the group sizes are approximately equal. There's another assumption for the one-way ANOVA, which is the same as the independent samples t-test. That is the assumption of homogeneity of variance. The variance in each of the levels of our factor should be approximately equal. We can use a Levene's test to look for that. Step 2, we're going to establish the null and the alternative hypothesis. As with an independent samples t-test, which says that mu1 equals mu2, if we're comparing 3 groups, our null hypothesis will be mu1 equals mu2 equals mu3. Or the first sample is drawn from a population that has a mean equal to the population from which the second sample is drawn, which is equal to the mean of the population from which the third sample is drawn. They are all drawn from populations whose means are equal. Our alternative hypothesis, therefore, will be mu1 does not equal mu2 does not equal mu3. That brings us to step 3. Select a criterion for statistical significance. Now we're going to use that alpha level of 0.05. We can set that to 0.01, 0.10, to really any alpha level that we chose, but the typical value we use is 0.05. What that means is we are defining the F distribution that we're going to use. With our alpha level and the degrees of freedom that we can interpret from the raw data, we will know what particular F test we're going to use. In this case, the F test will have some value larger than 1, which is a critical value, a cutoff score. Anytime we get test statistics over that critical value, we reject the null hypothesis. There is a statistically significant difference. Now this is where I typically start telling you about one-tail and two-tailed tests. And this is where that falls apart, because we're using squared values with the F test, which means they can only be positive. There is only one tail in an F distribution. So we're not really doing one-tail, two-tail tests. We're just looking for overall differences. The F test is really a one-tailed test by nature, although we'll sometimes talk about it as a two-tailed test. That's kind of a wash at this point. Just know that anytime you do an F test, it's always going to be a one-tailed test, or we're only looking for differences in one direction. The degrees of freedom are going to be determined by qualities within our model. Remember, we have an F test, which is a ratio, something divided by something else. So we need degrees of freedom in the numerator and degrees of freedom in the denominator. The degrees of freedom for the numerator will be the degrees of freedom between, which is k minus 1. K is the number of groups. In our example, we have 3 groups, so k minus 1 equals 2. The degrees of freedom within is the degrees of freedom for our denominator, and that is n minus k. The total number of participants is 21 minus our 3 groups. The degrees of freedom within is 18. Now that's all we need to know for defining our F distribution. So with alpha of 0.05 with 2 and 18 degrees of freedom, now we can figure our critical value. But let's just be clear, when you add those 2 degrees of freedom together, you get the degrees of freedom total, which is n minus 1, 21 minus 1, or 20. The critical value is based on an F distribution with an alpha of 0.05 and 2 degrees of freedom, between and within. There are 2 ways that you could determine the critical value. One is you could go to an F table and look up that number. The second is you could use the Excel spreadsheet that I've given you, and there's a special place in a formula that will calculate this for you. There is an F table in your spreadsheet as well. So here's how you use this. Degrees of freedom between is here in the columns, and degrees of freedom within would be the rows. We have 2 degrees of freedom between. So we're going to use the column for 2 degrees of freedom between. And we have 18 degrees of freedom within. So the confluence of 2 and 18 gives us a critical value of 3.55. The critical value with 2 and 18 degrees of freedom for this F distribution, 3.55. And there's another way that we could get this value, and that is simply to go to the spreadsheet. I've plugged in 0.05 as my default for alpha, but you can change that from 0.05 to 0.1 or 0.10, and then simply plug in degrees of freedom between, degrees of freedom within, and it will give you the critical value. If you're interested in how we get there, here's the formula that I'm using to calculate the degrees of freedom. Within this spreadsheet, you can always click on any particular box. You can extrapolate what the formula is that's being used. So there's no magic about it. The formulas are there. I'm simply designing it in a way where it makes it easier to plug in numbers and get the answers that we're looking for. Step 4, calculate the test statistic. This is where we get to have some fun. So be sure that your spreadsheet is open. We are going to ask the research question, does exercise improve health ratings? We have 1 factor, which is exercise. There are 3 levels of intensity in our exercise factor. Our dependent variable is overall health ratings, and that is on some scale that is measuring how healthy the individual is. And we've put all of that information into this table. So there is 1 group that exercises not at all, and here are their health ratings. For the moderate exercise group, we have other health ratings, and for the intense exercise group, still different ratings. Each of these numbers are different from other numbers. There's differences within the groups. There's differences between the groups. We're going to sort that all out with our one-way ANOVA. So here's how we're going to do that. Go to the Data tab. In the Data tab, you'll see the raw data that we're going to use for this ANOVA. So get that raw data, copy that data, be sure you get the headers, the none, the moderate, the intense, get our numbers, and now click back to the ANOVA spreadsheet portion and paste those values into the space where those numbers go. There's one more thing that we need for this to run, and that is to set the alpha level. So we'll set that at 0.05 here in the settings. And now we can see all of the findings, and then we'll cascade out and through. And you can also click on various cells if you want to see how these numbers were created. Let me focus on a few elements of the spreadsheet. So first of all is where you set the alpha level. Again, it can be higher or lower, but we're going to keep ours at 0.05. Below that, you see the settings. Here's the mean for each group. We're going to look for differences between the means, the mean differences a little later on. We have the sums, we have the sum of squares. All of these calculations are necessary for getting to the numbers we really need. And then they're all nicely organized in this ANOVA summary table, which is also a Times New Roman font, 12-point font. And you could literally copy and paste this somewhere else into Microsoft Word or wherever you're creating your write-up. You could take directly out of this spreadsheet and use it like that. Okay. We can see our degrees of freedom. We can see the source, the between and within. There's our sum of squares. The mean square is sum of squares divided by degrees of freedom. The F value is the mean square between divided by mean square within. It is a 5.74. That means there is 5.74 times more variability between than there is within. And that associates with a probability of 0.012, which means that we can interpret these findings. Is there a statistically significant difference? Remember our critical value. With 2 and 18 degrees of freedom is 3.55, but our test statistic is 5.74. 5.7 is larger than 3.5. Our test statistic is over the fence, statistically significant. We could also look at our p-value. It's 0.012 or 1 penny, which is less than a nickel. The probability is less than 0.05. All of this telling us exactly the same thing. There is a statistically significant difference. There are mean differences that are statistically significant inside of our model. The problem is we don't know where those differences lie, and in order to find that out, we would need to do a post-hoc test. Now, as I've said before, we're going to use Tukey's honestly significant difference post-hoc test. This is something that we can do very easily in JASP. I want to show you the steps we would go through for doing this in Excel. We're calculating a single value that if the mean differences are greater than this single value, they are honestly significantly different. This requires using a Q table, which is also in your spreadsheet. So if we're doing this by hand, the first thing we want to identify is how many treatments we have. This is not K minus 1, total number of treatments. In our case is 3. Now the degrees of freedom within, that is the total degrees of freedom within, which is 18. So with 3 treatments, 18 degrees of freedom, we have a Q value of 3.61. Now that's not our HSD value, that's the Q value that we're going to have to plug in to this formula. So notice I'm going to take my mean square within 7.78, plug that in, over n sub k, which is the level sample size for any particular group. In our case, all of the groups are the same size, so just pick a group. How many are in that group? Of course, if you're doing an ANOVA where the groups are different, we couldn't do this particular test by hand. We just don't have what we would need. We have to use a different type of test, and I haven't given you all the formulas for that. So I'm going to plug in my 7.78 and plug in my sample size of 7, and I get a HSD value of 3.80. In other words, any mean differences, you compare A and B, B and C, C and A. If that mean difference is greater than 3.8, then it is honestly, statistically significantly different. Let's compare mean 1 and mean 2. The difference is 4.14. That's greater than 3.8, so it is significant. Comparing means 1 and 3 gives us a mean difference of 4.57, which is also greater than 3.8, also significant. However, the difference between means 2 and 3 is a 0.43, which is not larger than 3.8, so it is non-significant. Let's remember our groups. Group 1 was the control group. Both of the exercise groups are significantly different than the control group. So exercising 2.5 hours a week or 5 hours per week is better than not exercising. However, when we compare groups 2 and 3, the 2 exercise groups, a non-significant difference. In other words, exercising 2.5 hours per week is ideal. Exercising twice as much does not give you a significantly different benefit over just doing the recommended amount. You can see the effect sizes in this box. I've included eta squared, partial eta squared, and the omega squared. Remember that our eta squared and partial eta squared will be exactly the same in a one-way ANOVA. I didn't bother putting in partial omega squared because it's going to be the same as omega squared. So we can use either of these 2 values. I would recommend using omega squared, which you'll notice is a little bit smaller, 0.311, than the eta squared, which is a 0.389. So now we can interpret the findings and do the write-up. We know there was a statistically significant difference among the groups. We identified which groups are different from which other groups. Let's write this up. A one-way ANOVA was conducted to determine whether the Mayo Clinic recommendation for 2.5 hours of exercise per week actually represents an optimal level of exercise for overall health outcomes. Independent groups of participants were tested at 2.5 hours of exercise per week, 5 hours per week, and a non-exercise group was used as a control group. There was a statistically significant difference among these 3 levels of exercise on overall health ratings. And we can see the example of the statistical write-up. Post-hoc testing with a Tukey HSD revealed significant differences between both exercise groups and the non-exercise group. However, the high-intensity exercise group did not have a statistically significantly higher overall health rating than the moderate exercise group. These findings support the Mayo Clinic recommendation that moderate exercise of 2.5 hours per week is optimal. Better than no exercise, but not better than intense exercise. So knowing t-tests is great, but we need something more if we're going to explore all of the possibilities in statistics. So next week, we're going to learn about ANOVA models. We're going to do a one-way ANOVA. We're going to do a blocked ANOVA. We're going to do a two-way ANOVA and explore all the different varieties that are available for us to really explore the world and learn how to do these tests properly. Thanks for being here, and I'll see you guys next week.